this is, we study under the title of weak or strong duality. So, okay. So let's just note down what is the primal problem again. So it's minimize f of x such that c of x greater than or equal to 0. This is our constrained optimization problem. Okay. Now let's see what we say about the dual problem. Okay. So let's take for any feasible x bar. Okay. Feasible x bar just means it's any regular guy in the domain of the constraint set. It need not be the best x. Okay. So any feasible x, okay, and any lambda bar greater than 0, then the following holds. So I'm going to note one statement and which we will prove. Okay. So q of lambda bar so what is this saying? That take any feasible x bar, okay, and take any lambda which is greater than or equal to 0, then the value of the dual problem is always less than the value of the primal problem. So this in itself does not look very interesting, but because we have an inequality, we can make this inequality even stronger. For example, I have left hand side less than or equal to right hand side. If I want to make it really tight, what is the tightest I can do on the right hand side? A minimization operation or a maximization operation? Minimization operation. And on the left hand side, maximization operation. And remember, what was the definition of Q? Q had a minimization operation going on, right? So let us define f star as the infimum of f of x such that x belongs to the constraint set. Instead of infimum, you can also just think of it as a minima, and we'll write q star as the supremum of q of lambda, lambda greater than or equal to 0. Okay. Now if I can if I substitute f star and q star into this inequality, is it still correct? It is correct, because the right hand side I have made as small as possible, the left hand side I have made as large as possible. So this is really something that is very interesting. Okay. So when I minimized f, I made f as small as possible while x still belonged to the constraint set. Isn't that the solution to the primal problem? Right? That is what I was looking for. Give me the smallest f such that x belongs to the constraint set. So therefore, this is the optimum of the primal. Q of lambda, once I got the q of lambda in our two-step process, once I defined q of lambda, to get the dual solution, what did I do to q? I did a maximization problem. So this q star is what? It's the solution to the dual problem. So this is the optimum of the dual problem. Right? So there is an inequality here that the optimum of the dual problem can at best reach the optimum of the primal problem. So this is a very, very important result in duality. Oh, why is this statement true? Yeah, I'll prove it. We'll prove it now. Okay, I thought I'll just give you the implication and then we'll get to the proof. Right? So this is the implication. The proof is actually also very simple. Okay, so let's look at the proof of this. Okay, so we just go to the definition of our, we go to the definitions of Lagrangian dual, Lagrangian and so on. So the definition of this was minimization over x gives me my Lagrangian dual function. Okay, and this is essentially, if I just substitute the definition of this guy, this is the definition of the Lagrangian function. Okay, everyone agrees with this. Now I am going to put a box over here for you to fill in equal to, less than, greater, whatever. Less than or equal to, right? Because the top thing is the minimum. So if I am not at the minimum, the value of this guy is going to be less than or equal to f of this, right? Because and x is simply feasible. Okay. So this gave me q of lambda bar is less than or equal to this, right? Now, did I put any constraint on lambda? I said lambda greater than equal to 0, right? So lambda is greater than equal to 0. What about c of x bar? Is there an inequality on that? It's also greater than equal to 0. So therefore, what is this term? Always greater than equal to 0, right? So therefore, this whole term, and I can get rid of a minus term, the inequality would still hold, right? So surprisingly, the proofs in the world of duality are very simple. We just use definitions of concavity, convexity, and so on, right? So it's clear what we did. We took the definition of the Lagrangian dual function. We substituted any feasible x with inequality holds. Then I noted that the constraint is always greater than equal to 0. I'm saying that this holds true for lambda greater than equal to 0, and then I'm done. Okay. So this holds. So this gives us a very important couple of points. If q star is strictly less than f star, q star and f star are the optimum values, right? Then f star minus g star is obviously greater than 0. This is called the duality gap. Okay. When there is a duality gap, this is also called weak duality. The second case is if q star is equal to f star, no gap, this is strong duality. Okay. And the final statement I'm going to make over here, without proof, I'm going to state it, but this is one of the major things that distinguishes convex and non-convex optimization. For convex problems, the duality gap is always 0. For convex problems, let's just say always strong duality. Okay. So in so always strong duality, there is one small, this is a star which is their terms and conditions. So there's one terms and condition over here. It is the same thing that we have encountered earlier between the discrepancy between algebra and geometry, if you remember. That discrepancy needed one small screwdriver to tighten it, which was what? Constraint qualification. Same thing holds over here, that this strong duality holds under constraint qualification, right? So we'll just mention this as a star under and an example of constraint qualification we studied in this course is LICQ. Okay, there are other types also, but if this holds, the statement of strong duality also holds. Okay, so this is why in the convex world you can solve the primal problem, you can solve the dual problem, you will reach the same optimum value, right? So you have that choice which way to approach it. If you have a non-convex problem, solving the dual problem is still not too bad if you have nothing else going on. If the primal problem is very, very difficult to solve, at least the dual problem will give you some kind of a bound on the function value, right? You know that the supposing you solve the dual problem, you get Q star. You know that the solution to the primal problem can never be what? Below that value. So that may be useful information in many problems. So, right? Okay, so that's what. So this is essentially what I wanted to cover about duality and the difference between convex and concave problems. And as you've seen, the example, I mean, the proofs are really simple. Yeah, question. Hmm.
Let's say we are solving the dual problem.
Hmm.
There will be a duality gap.
Correct.
We will find some x bar and some lambda star which is giving us the minimum in the dual problem. Whereas in the primal problem, it won't give us f star. It will give us some other values.
Yeah, that is the duality gap, f star and q star. That is the duality gap. So yeah, absolutely. So if I take the optimum value of x star and lambda star from the dual problem and substitute it back, I'm not going to get the optimum f. That is the meaning of duality gap.
But does it have any meaning of closeness to optimal value?
So question is there any notion of closeness? Unfortunately not. Unless you provide some further information in the problem, we cannot quantify how small is this gap. Okay. And yeah. So that is also an open area of research to quantify how small is this gap. Okay. Any other questions? Okay. So to kind of drill in this idea of primal problem, dual problem, again I'm going to, this is more like a tutorial, we will work through a problem, solve it together so that we get a feel for the dual problem. Primal problem we have spent most of the course working on, so we need not spend more time in. But the dual problem can often be a little bit, because it's a two-step process. First is a minimization, second is a maximization. So many times it's like solving two optimization. It is actually solving two optimization problems. One is a minimization, the second is a maximization. So you need to have a little bit more patience in working with it. Okay. So let's take an example. Okay, so I'm going to take an example whose primal problem is just graphically I can see it and tell. Okay. So minimize, let us say. So you might encounter problems like this, minimize minus x1 plus x2. In fact, in the tutorial there was one such problem. There's no problem, right? I mean, minus is there, so what? It need not always be with a plus sign. Subject to, let us say, this is my primal problem. Okay. So constraint 1, what does it look like? Interior region of a circle. Right. So if I were to sketch this, radius 2 root 2, right? And so one region is over here. What is the second constraint? Below, right? x2 less than equal to 6. So will this line cut the circle or be above or below? Above. Right. What is 2 root 2 roughly? 1.4 to 2.8 something, right? Right. So this is 6 over here. Okay. So this guy is saying that you should be below here, right? So what is the effective feasible set? It's just the interior of the circle. Okay. So the second constraint is kind of redundant. Okay. And now what are what are the contours of the cost function? Straight lines with slope minus 45. We have seen this before, right? Like this. So in this case, where is the solution? topmost, right? Because there's a minus sign associated with x1 plus x2, so the solution is sitting over here, right? This is because at this point minus x1 plus x2 is minimized, right? What is that minimum value? Minus 4, right? Because this point has coordinates of 2, 2. Therefore, f star is equal to minus 4 and x1, x2 is equal to 2, 2. This is just graphically, we didn't solve any Lagrangian to get it. Okay, so now let's solve the dual problem. Okay, two-step process. So first step I need to first form the Lagrangian, right? So Lagrangian of x comma lambda is equal to f of x minus lambda I ci summation. Okay, so this becomes a little bit longer to write. So minus x1 plus x2, that's my f. Okay, and then I have my constraints. So c1 and c2 are there, so I get a minus lambda 1 8 minus x1 squared minus x2 squared and minus lambda 2 6 minus x2 greater than 6. This is my Lagrangian. Okay. So if I extract a minus sign common from all of this, do I have a quadratic in x1, x2? Right? So what are the coefficients of maybe I don't need to extract a minus sign. So let's just write down x1 squared. What is the coefficient? Lambda 1, x2 squared, lambda 2, and then I have x1, x2 terms. So what is the x1 term? Sorry, x2 squared is also lambda 1, correct? Lambda 1. What is the x1 term? Minus x1. What is the x2 term? So it's let's write here x2 multiplied by 1 minus lambda 2, right? And any constant terms? Minus 8 lambda 1 minus 6 lambda 2, is that right? Any mistakes in this? Looks okay. So is this does it make for us to minimize? So this is a quadratic function. The only quadratic function that it makes sense to minimize is a what function? A convex function. Is this a convex function? Yes, because right. So it's an upward opening parabola because lambda 1, lambda 2 greater than equal to 0. Why are lambda 1, lambda 2 greater than equal to 0? Because these are inequality constraints, right? So these are all the subtle points. If it were an equality constraint, I cannot say that, right? So this is convex, therefore makes sense to minimize this with respect to x. Otherwise, it does not make any sense. Okay. Okay, so q of lambda is going to be the minimum with respect to x of this, right? To get this, I would take the gradient with respect to x1, x2, right? So what is grad of the Lagrangian with respect to x? So derivative with respect to x1, what will I get? 2 lambda 1 x1 minus 1 is the first term, and 2 lambda 1 x2 minus 1 minus lambda 2 is the derivative with respect to x2, and I should do what to this? Set it equal to 0, right? So when I set it equal to 0, what am I looking for in this? I want to find the values of x. I want to eliminate x from this guy, so I will find out x from here. Okay. Alright, so x1 star is going to be equal to 1 by 2 lambda 1. x2 star is going to be, can you tell me what is x2 star? 1 minus lambda 2 divided by 2 lambda 1. Okay. So I've done my part 1, right? I've basically got my x star, and now I can substitute and get q of lambda, right? So q of lambda is going to be, so I need to substitute this x1 star and x2 star into that q expression in order to get it, right? So q of lambda, let me write down the expression over here, lambda 1 x1 squared plus x2 squared minus x1 plus lambda 2 minus 1 x2 minus 8 lambda 1 minus 6 lambda 2. Just rewritten it. And now I need to substitute this into this expression. Right. So this is going to be, so when I put x1 squared plus x2 squared, I substitute this, what am I going to get? 1 plus 1 minus lambda 2 whole squared. What about the denominator? What is the denominator? 4 lambda 1. That's the first two terms. Okay. And then I want to keep 4 lambda 1, let us say we want to keep as a common denominator. So minus x1 will become minus 2. Then, okay, then I have x2, right? Now x2 multiplied by, so this will become 1 minus lambda 2 whole squared, right? That's this term. And then I have a 8 lambda 1 and a 6 lambda 1, sorry. There is going to be a 2 somewhere, right? So there's going to be 2 here and there's going to be a 2 here, right? Let me just write it nicely. Oh, actually, these guys can just remain as they are, 8 lambda 1 minus 6 lambda 2. Is that right? Yeah? The last two, it's not in the numerator. The line ends over there. Okay, so alright, so this is what it is. Okay. Now step 2. So it's some not a very convenient looking form, but it is what it is. So what is step 2? Once I get q, what do I do with it? Maximize it. Right now, step 2. Solve. Right. So max lambda has to be greater than or equal to 0. Q of lambda. Now again, to verify that we should do this step actually, to verify that maximization makes sense, you have to convince yourself that this function that I have is actually concave, then maximization will make sense. It's a function in 2 variables, so we can verify concavity by looking at its Hessian. That is one straightforward way of doing it, okay. You could also complete the squares and show that it's a concave function. So all of that. So let's assume that we have checked concavity. Okay. Okay. So let's do this. So I've done a little bit of algebra to speed this process along. There are a whole bunch of minus signs that you can see in the definition of Q of lambda. So I'm going to pull those minus signs out. If I pull a minus sign outside, what happens to maximization? It becomes a minimization, right? So I'm going to skip a few steps of algebra just in the interest of time and remove that minus sign, which flips the max to min. Okay, so that's all I've done. So I'm going to write the final expression that I get. So minimum
You got x1 star and x2 star in terms of lambda and lambda.
correct
And you're substituting that in the expression.
in order to get Q.
But now x1 star and x2 star should also satisfy c1x greater than 0 and c2.
I can't verify that independently unless you tell me what lambda is.
That is, but wouldn't that impose some conditions on lambda?
Uh,
As of today, only condition which we have is lambda greater than or equal to 0.
correct.
Because of this, or there be some additional conditions.
So in the way that we have formulated the dual problem, which we did without proof but just with geometric intuition, we did not impose something extra. It turned out that the second recipe gave me the same answer.
But even in the dual problem, we told that you have to minimize over x belonging to sigma in the first optimization.
Correct. So we'll have to check once again whether, I mean, we'll check whether or not this. Yeah. Okay, so we have proved, yes. So why am I doing it again? Just for practice. We know that Q is going to be concave, but it's a simple enough example for you to verify. You don't have to verify it each time. Okay. So when does it help to verify? It will help to verify if you have made some simple mistake in algebra, right? So some simple steps, these are the things which help to catch your own errors, that you see, oh hey wait, this is not turning out to be concave, maybe let me walk back a few steps. Okay. So this is what this whole problem ends up being. Okay.